This is an attempt to explain Dijkstra's algorithm by solving the Leetcode 1514 problem, path with maximum probability. So you're given an undirected weighted graph of n nodes, zero indexed, represented by an edge list, where edges of I is equal to a comma b, right? So which means that edges of 0 between 0 and 1 uh, is an undirected edge connecting the nodes A, B with the probability of success of traversing that edge of success prob of I, right? So 0 to 1 is the probability of success of traversing that edge is 0.5 as mentioned here, right? And then 1 to 2 is 0.5 and 0 to 2 is 0.2. So given two nodes start and end, find the path with maximum probability of success to go from start to end and return its success probability. There is no path. If there is no path from success start to end, then return 0, right? Then there is obviously no path between start to end, right? So the probability of success of traversing between those between uh, start and end will obviously be 0, right? So let us consider two examples to understand this better. Okay, so 0, 1 and 2. Okay, the first example given is 0.5, 0.5 and 0.2. Okay, so this is start and this is end. Okay, from here to here we have to find out the maximum probability. Okay, so let us consider a array called probability. Okay, and that array will be initialized to 0, 0 and 0 because there are three nodes here. Okay, index 0, index 1 and index 2. Okay, so what we'll do is let us start with the start index. Okay, start is 0, so probability of start, let us make it to 1. Okay, probability of start is 1, and now uh, we'll have to start with the start index. Okay, so start node here. Okay, start node has two adjacent nodes, two neighbors, which can be connected uh, through this or this, right? So it will be like we have two choices. We can go from 0 to 1 and it has a success probability of 0.5, or we can go from uh, 0 to 2 and it has a success probability of 0.2. Okay, so what we'll do is we'll put both of these into a heap, into a priority queue. This is a max heap. Okay, so this will pick the one with highest probability. Okay, the highest probability is 0.5 here, so this one will be picked. Okay, so when we poll an element here, this will be polled. Okay, we have started from 0, which is this one, so this is the one we have traversed to. So right now uh, we are at uh, we are at 1. Okay, and the probability of 1 is 0.5 as mentioned here. Okay, and the probability of 2 is 0.2 as mentioned here. Okay, first let us change that because 0.5 is obviously better than 0 and 0.2 is obviously better than 0. Okay, the probability of 1 is 0.5, and we have two choices from here. We can either go back to 0 or we can go to 2. Okay, so if we go from 1 to 0, then the probability would be 0.5 into the probability of 1 is 0.5, and the success probability from 1 to 0 is also 0.5. So 0.5 into 0.5, which will be 0.25. And we have another choice, which will be 1 to 2. 0.5 is this probability of I, or probability of the first node here. And from 1 to 2, the success probability is 0.5. So 0.5 into 0.5 will be 0.25. Okay. So here, what we'll do is we'll place both of these as well into. Okay, so first of all, we already know that the probability of 0 is 1. Okay, so when we already have a 1, which is a much better probability, why would we choose this option? As in, why would we go from 0 to 1 and then come back to 0 and say that the probability is 0.25 and we have a better choice of 1? Okay, so we would simply ignore this and we would add only this one into the heap. Okay, so right now we will add 2 0 to sorry 1 to 2 and 0.25 into the heap, and this has been removed. So we have two items here, so I'll just clean it up a little. Okay, we have these two options in the heap, uh, and right now we would choose, okay, this is 0.25. Okay, we would choose 0.25 because 0.25 is better than 0.2. Okay, so we would choose this, and then uh, so this is 0.25, this is obviously better than 0.2, so let us change this here. Okay, now we are at 2, we are at 2 and the probability of 2 is 0.25. We have two choices from here. We can either go to 0 or we can go to 1. Okay, if we go to 0, then the probability would be 0.25 into 0.2. Whatever it is obviously less than 1, so we would ignore this. Okay, and again 2 to 1, 0.25 into 0.5, 0.25 into 0.5. Okay, whatever it is, we would ignore this also because it will be less than uh, what we have for 1, which is 0.5. Okay, so we wouldn't add anything to the heap right now. So that will be the end of the problem here. So we would return the probability of the end is 2 here, so probability of 2 is 0.25. We would return that. That's the solution. Okay, so let us consider another scenario wherein we have 0, 1 and 2. This is 0.3, this is 0.5, and this is 0.5. Okay, so we'll start here and end here again. So the probabilities will be 0, 0, 0 initially, 0, 1, 2 indices, and then the probability of start, which is probability of 0, will make it as 1. Okay, and then we have two choices from here. We can go to 1 or we can go to 2. Okay, if we go to 1, then the probability would be 0.5 into 1, and if we go to 2, the probability will be 0.3 into 1. So this is 0.5 and this is 0.3. So we'll place this into the max heap as said earlier. So 0 to 1 and 0.5 and 0 to 2 and 0.3. Okay, so 0.5 is a better choice here, so we would choose that. So this we have come from 0, then will come from 1. Right now we have two choices again. We can go 2 or 0. Okay, 1 to 0, 1 to 2, and 1 to 0 would obviously be 0.5 into probability of 1 is right now 0.5. We haven't replaced that here. Okay, this is 1 as we did here, and this is 0.5 and this is 0.3 so far. Okay, so the Uh, 1 to 2 would be 1 to 2 is 0.5 into 0.5, and 1 to 0 would be 0.5 into 0.5. So this would be 0.25, this would be 0.25. For 0, we already have 1, which is a better choice, so we would ignore this. For 2, we have a better choice of 0.3 here, so we would ignore this as well. So this is the only item that is present in the heap right now, so this will be chosen next. So we will be at 2, and from 2 we have again two choices, 2 to 0 and 2 to 1. Okay, from 2 to 0 it is 0.3 into probability of 2 is 0.3 into 0.3, so we wouldn't want to choose this. And then we have 2 to 1, which is 0.3 into 0.5, and we wouldn't want to choose this as well. So here ends the problem. So we would return the probability of 2, which is 0.3. That's it. Okay. So earlier we have added 0.25 as well, but here we wouldn't add it because 0.3 is already a better choice than 0.25. Okay. So let's try solving this in Leetcode and try and check optimal R solutions. Okay. So let's also discuss about the time complexity and space complexity. Okay, so let us initialize a probability array. Okay, and then let us set the probability of start to 1. Okay, let us have a priority queue. Okay, and then uh, let us have an adjacent list. Okay, for which we would do this for int I is equal to 0, I less than n, I plus plus. Okay, it's not n, it's edges of dot length. Uh, so for adjacent list, we would need an array, right? So list of, so okay, so let me initialize this first. Okay. So what are we adding here? We are adding two items, which would be the edge that it's being connected to, and the success. No, I, we would do the opposite to 1 here. Okay. So this is how we generate it. Okay. So, and also we would like to compare this with. So this is a max heap. So let's do this. Probability of B will be compared to probability of A. Okay. So this is a max heap. So B comes first. So that the maximum element comes first. Okay. So let's add this into the max heap first. Let's start with the start index. Okay. Okay, let's name it as current. Okay. Uh, so we would want to add it only if it is a better choice, right? So how do we define if it is a better choice? If the probability of the neighbor that we have got right now is, if the probability that we generate right now, so the probability that we generate would be the probability of current into the success probability of the neighbor's connection we would get here. Okay. If it is a better choice, then probability of equal of 0 is equal to whatever we have here. Okay, we are calculating the new probability we would get here, and we are checking if it is a better choice. If it is a better choice, then we are adding it here, and not just that, we are adding it to the max heap. Okay. Okay, so what do we need to add here? We have added start here. So similarly, we would add the neighbor of start. So neighbor of start would be this one. Okay, and then we would return the probability of end. Okay, that's it. Let's check if it is fine. Okay, legal start of expression. I've added an extra plus. This is a typo. Okay, what is this? Converted to int edges of I. Oh, so edges of I, and okay, this also has to be okay. And we are trying to compare it with this, but this is actually double. So okay, this should solve a problem. Okay, so it's okay for all these conditions. So it should probably be okay for the submission as well. Okay, let me check. Hmm. Okay, it is better than 88% of the solutions, so it should be fine. So discussing the time complexity and the space complexity. Uh, so okay, so we will have to store all the edges here, so if we have say three vertices, we may have at most uh, like one edge from 0 to 1, one edge from 0 to 2, and one edge from 1 to 2. So if we have n edges, n nodes, then we might have at most n square edges. So the space complexity would be O of e, wherein e is the edge. So e represents edge, so we will have to store all the edges. So that's the reason we'll have space complexity of O of e. And coming to time complexity, we will visit from start node. Uh, we might visit 1, and then we might visit 2 again, and then from 1 we will only visit 2, but we will never come back to 0, right? So we will visit through an edge only for one time, right? So it will be O of e, and then we will have to compute the maximum using a heap here, and that so we might add at most all the edges that we have, so that will be log e. Okay, so the time complexity would be O of e log e. uh, Log e is actually equivalent to log v. Why is it so? Because v is the, let us consider v to be vertex here, representing a vertices. So if we have v number of vertices, then at most we can have v square number of edges. So if e is equal to v square, then this would be equivalent to e log v, because O of log n square is equivalent to O of log n. That's the reason the time complexity would be this. Okay, thanks for watching.